imagine your data is a glowing cloud in space. PCA asks a surprisingly visual question: if you could shine a light on that cloud, which shadow would keep the most information? First, PCA recenters the data by subtracting the average point. That moves the cloud to the origin, so we study its shape, not its location. Then it builds a covariance matrix, usually written C. Covariance measures which coordinates tend to move together. A stretched diagonal cloud means two features rise and fall as a team. The key equation is CV equals lambda V. The vector V is a direction that the covariance matrix does not twist away from. Lambda tells us how much variance, or spread, lies along that direction. The largest lambda gives the first principal component, the axis where the cloud is widest. Projecting every point onto this axis gives the best one-dimensional summary in the least squares sense. In plain language, among all possible lines, it loses the least squared distance from the original points. Add the second principal component, perpendicular to the first, and you capture the next biggest spread. In high dimensions, PCA simply ranks directions from most variation to least variation. That is why PCA is useful for visualization, compression, and noise reduction. It does not discover meaning by itself, and high variance is not always importance. But as a first map of a complicated dataset, PCA is elegant. Rotate the coordinate system, sort the shadows, and keep the ones that still tell the story.